Oh, I'm already recording. Cool. Okay, so let's dive into this. Hopefully, this will be helpful for some of us as we read through it. So, a company manufactures model rockets that require igniters to launch. Once an igniter is used to launch a rocket, igniter cannot be reused. Makes sense. Sometimes an igniter fails to operate correctly and the rocket does not launch. The company estimates that the overall failure rate, defined as the percent of all igniters that fail to operate correctly, is 15%. So, probability of a failure is 0.15. A company engineer develops a new igniter called the super igniter with the intent of lowering the failure rate. To test the performance of the super igniter, the engineer uses the following process. One igniter is selected at random, used in a rocket. If the rocket launches, another super igniter is selected at random and used in a rocket. And this is repeated until the process stops. So the process stops when a super igniter fails to operate correctly. So this is making me think geometric, right? So this is the idea of a first success if the success is actually failure. Or 3, 2, have successfully launched, whichever comes first. Assume the superigniter failures are independent. Ah, good. Sweet. If the failure rate of the superigniters is 15%, what is the probability that the first 30 superigniters selected using the testing process successfully launches? So assume, right, that the probability of failure is equal to 0.15. Probability of 30 launches then would equal 0.85 times 0.85 times 0.85. I think you get the picture. Times dot dot dot, right? Notice the launch is the complement of failure, so that'd just be 0.85 30 times, or where was that? 0.0076. Sorry, I was looking at this earlier and forgot to record. There we go. Okay, B. Given that the first 30 superigniters successfully launch, what is the probability that the first failure occurs on the 31st or 32nd? Now, this is weird language. So, given that the first 30 successfully launch, but these are independent events. So, if we're assuming or given that the first 30 launch, the probability that the first failure is on the 31st, we no longer have to worry about the first, second, third, etc. We just have to worry about the 31st. Or in this case, it would be the first. Interesting. So what we're really looking at is what's the probability that the first failure is the first trial, or that the first failure is the second trial. And so probability of failure is 0.15, which again in this case would be success. And then x equals 2, that'd be one failure. And then we would finish with a success. And so that comes out to be 0.2775. One thing I do want to point out is if you go through this idea, all right, and you recognize, hey, this is geometric, and it's a CDF, right? Probability of success is 0.15. The lower bound is 1, the upper bound is 2. And I know this may feel weird because what we're really looking at is 31st and 32nd, but we already know the first 30. I guess that's a good way to think about it. The first 30 have already happened. They're no longer random variables. It's already happened. So we're only looking at the first and the second. Okay, so there we go. Let's try that. 0.2775. That's what I got from those calculations as well. Okay, but notice geometric CDF would have probably made that a lot easier. So given that the first 30 superigniters successfully launch rockets, is it reasonable to believe that the failure rate of the super igniters is less than 15%. Okay. So the probability then that X is greater than or equal to 30. Because what I'm thinking about, if I'm looking for reasonable to believe this, I'm thinking, is that statistically significant evidence? Statistically significant. And so when I think that of statistical significance, I'm thinking at or more extreme. So what's the probability that X is greater than or equal to 30? And we're again thinking geometric CDF. So let's go back to here. Now this time, um, I'm actually going to look at greater than or equal to 30. I went to the wrong spot. Probability, distribution, CDF, 0.15, 30, 32. Yep. So the probability that it's 30 or more trials or 30 to 32 trials would equal 0. I wonder if it really should be 1 minus the probability of 30. Let's do that. Minus 1 to 29. Yeah, slightly different answer because you stop if it's 32, right? Like we don't go anything beyond that. Um, so that would equal 1 minus. So if you're wondering like why I switched it, the idea is that technically a geometric distribution can go on for forever, right? So, but this is stopping at 32 no matter what. So we don't get the option of 33, 34, 35, etc. So if I do 1 minus probability that X is less than 30, that'll actually give me a more accurate probability. Was it 0.00897? So 90. Okay. So the likelihood of 30 or more rockets launching successfully is 1 less than 0.05, right? Remember, that's my level of significance. 2, so unlikely I, by random chance alone, I don't believe probability of failure equals 0.0 or 0.15, probably less. All right, let's check against the rubric here. All righty. So yeah, 1 minus 0.15 raised to the 30th, 0.0076. So given there are no failures in the first 30 trials, probability of the first failure, that's right, because the first 30 wouldn't matter at all anymore. The probability that there's a failure on the 31st is just 0.15, right? That does not occur on the 31st, but on the 32nd, it's just one more failure and then one more success. Yep, that looks good. So the result of the probability calculation part A provides a reason to believe that the failure rate is less than 15%. The calculated probability shows there's a less than 1% chance that 30 or more igniters in a row would not fail. And I don't fully agree with that. Okay, let's see. correct probability and correct justification. Sweet. So you had to have some work in there. Part B gives the correct probability and correct justification. Okay. So you had to have some work in there. Could have referenced a geometric CDF, I bet. It's reasonable to believe that the failure rate is less than 15% and bases this decision on the fact that the probability of 30 consecutive successful launches with a failure rate of 15% is small and does so in the context of the situation. I think interesting. So you had to link um, probability and significance level. Granted, we haven't studied that yet, so I wouldn't sweat it. Okay, I would accept what I did. All righty, last one for now. So this one's an interesting one. I have worked this one before. A local arcade is hosting a tournament in which contestants play an arcade game with possible scores ranging from 0 to 20. The arcade has set up multiple game tables so that all contestants can play the game at the same time. Thus, contestant scores are independent. Ah, important. Each contestant's score will be recorded as he or she finishes, and the contestant with the highest score is the winner. After practicing the game many times, Josephine, one of the contestants, has established the probability distribution of her scores shown in the table below. Cool. Crystal, another contestant, has also practiced many times. The probability distribution for her scores is shown in the table below. Calculate the expected score for each player. It doesn't ask for work, but my guess is that they want work. So I'm at least going to do this. I'm going to call this expected value of Josephine is the sum of x times probability of x. And if you're unsure, remember, we have a formula sheet. These are discrete random variables. And so I got a formula sheet for that. Do I have it pulled up? I don't think I do. So don't forget, expected value, same thing as the mean, but discrete random variable, sum of x times probability of x. Okay. So just 16 times zero point 0.1 plus 17 times zero point 0.3 plus 18 times zero point 0.4 plus 19 times zero point 0.2 equals something. The expected value of crystal is equal to 17 times 0.45 plus 18 times zero point 0.4 plus 19 times zero point 0.15. Okay. And so let's go to the calculator because I don't feel like doing that. So list and spreadsheets. So I've got crystal. I've got the probability of crystal. Let's go ahead and do her values. So 17, 18, 19, 0.45, 0.4, 0.15. Yep, that makes sense. So I'm going back and just making sure that probability adds up to 1. Stat calculations, one variable. My variable is crystal. My frequency list is the probability of crystal, and there we go. So 17.7. And that honestly, that number makes sense. The vast majority of the data is between 17 and 18, and even more is in the 17, almost half. So it makes sense. All right. And then now I'm going to do Josephine. Probability of Josephine. So she was 16, 17, 18, 19. And this was, oh, and the probability is 0.1, 0.3, 0.4, and 0.2. Did not want linear regression. So now Josephine, probability of Josephine. Oh, and that's also 17.7. Huh. If I have time, I might go back and check that. Okay, suppose that Josephine scores 16 and Crystal is 17. The difference, Josephine minus Crystal, is -1. List all combinations of possible scores for Josephine and Crystal that will produce a difference of -1. So Josephine, Crystal would be 16, 17. Josephine and Crystal, a 17 and an 18. And Josephine minus Crystal would be 18 and 19. Those are the only ways to get a -1. Cool. Oh, and the probability for each combination. Now they are independent, right? Yep, independent events. So for this would just be so probability that Josephine is a 16 and Crystal is a 17. Those are independent events, so I can just do zero point 0.1 times 0.45 and get 0.045. The probability that Josephine is a 17 and Crystal is an 18 is zero point 0.3 times zero point 0.4 or 0.12. And the probability that Josephine has an 18 and Crystal has a 19 would be zero point 0.4 times zero point 0.15. That'd be 0.06. And I'm doing that off the top of my head, but definitely use a calculator. Find the probability that the difference is -1. So those are all the different ways to get -1. So the probability that Josephine minus Crystal equals -1 is quite simply uh, the sum of all those, right? So 4, 5 plus 0.12 plus 0.06. So 0.105, 0.12, 0.225. Starting to doubt myself. Really quickly, I'm actually going to pause this, make sure that everything is good to go with the class video from class today. All right, I'm back. I had to get the video going. Okay, so yeah, I'm pretty sure that's right. What's that, 0.165? Yeah, yeah, yeah. Okay, so D, the table below lists all the possible differences in the scores between Josephine and Crystal and some associated probabilities. So -3, what would that have to come from? Oh, 16 to 19, right? -2 can come from 17 to 19 or 16 to 18. The -1, okay, so we actually just did this. The probability that the difference is -1 is at 0.225. Now we could go through the same process up to this point, and how we got that -1, or we can just remember that I need a sum of probabilities to be 1. So let's do that quickly. 0.085. Cool. Again, that could have come from Josephine with a 16 and Crystal 18, or Josephine 17 and Crystal 19. And I wouldn't do this, but I'm just going to quickly check myself. So that'd be zero point 0.1 times 0.4. So that'd be 0.04. And then 17 is zero point 0.3 times 0.15. I believe it's going to be a 0.045. Yep, and the sum of that's 0.085. Cool. So notice multiple ways to approach it, but yeah, the complement there is definitely the easier route. So hopefully that was helpful, and you're seeing how to do some of these things a little bit better. Hope you have a great rest of your day, and I'll upload this as soon as possible. See ya.